everyone, welcome to this lecture. So, now we have seen oblivious transfer protocols. So, let us go back to the problem of pre-processing phase for the GMW protocol, and we will see the pre-processing phase for the GMW protocol for the simpler case of Boolean ring based on oblivious transfer, and for simplicity we will focus on the two party case in this lecture. We will then see in the next lecture how this method can easily generalized for the n party case. So, just to recall what exactly we want to generate here when we say the pre-processing phase. Our goal in the pre-processing is phase is to generate additively shared random multiplication triples, okay, where the A component, B component, C component, they should be random elements from the ring, except that the C component should be the product of the A and B component, and all the components of all the triples should be n comma t additively secret shared among the parties, okay, where the addition operation is as per the underlying ring, and we want to do in the dishonest majority setting, where all but up to n minus 1 parties can be under the control of the adversary. Okay. And we will see the original GMW method here, which was proposed for the special case where the ring R was the Boolean ring, where we have only two elements, namely 0 and 1. The plus operation is the XOR operation, the product operation or the multiplication operation is the AND operation, and this is based on oblivious transfer. And we will see first the simpler case of two party setting, where there are two parties and one of them could be corrupt. Okay. So, that means now if I rephrase the goal of the pre-processing phase for the two party case and for the Boolean ring, our goal is the following. We want to generate additively shared random multiplication triples, and by additive sharing I mean that each party should have the share of the underlying value, and there are two parties because I am talking about the two party case, such that the XOR of their shares should give you the underlying value. So, the A component, B component, C component, they are going to be bits. Okay. So, the A components, B components, C components, they are going to be bits. The A and B components are going to be random. The C component should be the AND of the A and B components, and this data structure has to be generated in such a way that corrupt parties shares should be independent of what exactly are the underlying multiplication triples. So, generating this data structure will be done in two stages. In first stage is for all the L multiplication triples which we want to generate, we generate first the A and B components in a secret shared fashion. Okay. Now, assuming that we have generated the A and B components in a secret shared fashion for all the L multiplication triples, we generate securely the C components again in a secret shared fashion. And generating the C components in a secret shared fashion requires instances of bit oblivious transfer. Namely, if I take the ith multiplication triple, then in stage 1 we have generated this data structure, namely we have generated a secret shared bit AI, a secret shared bit BI with none of the parties knowing the exact value of the bits AI and BI. And now in stage 2 we have to use the oblivious transfer protocols in some way, so that parties hold secret sharing of the bit Ci, where Ci is the AND of AI and BI. And in this process no additional information about the bits AI and BI should be revealed. Now, if we are doing this pre-processing, if we are doing this stage 1 and stage 2 computations in the pre-processing phase, the advantage is that the stage 1 as well as stage 2 for all the L multiplication triples that we want to generate can be executed in parallel, because they are completely independent of each other. So, now let us see first the stage 1, and what is the goal of stage 1? We want to generate the A and B components, the bits A and B for all the L multiplication triples in a secret shared fashion among the two parties, with no party knowing the exact values of the A bits and B bits. And for this we will use a protocol which I call as RAND extract. We had seen a RAND extract protocol for the case of Samir secret shared preprocessing phase. Okay, so, I have used the notation and called the protocol RAND extract for this GMW preprocessing as well. And this RAND extract protocol will help you to generate additive sharing of random values R, okay, where none of the parties will be knowing what exactly is the bit R, but the bit R will be secret shared as per the XOR sharing among the two parties. And since our goal is to generate L such A and B random values, but this one instance of RAND extract can give you one such random value, we can run this RAND extract protocol 2L number of times, because our goal is to generate L number of A bits randomly and L number of B random bits. Okay. So, we have 2L values to be generated. And before going further, I would like to stress here that the RAND extract process that we had seen in the context of secret sharing based preprocessing phase, it will not work for your Boolean ring or Boolean field, because there we require the field. First of all, it requires a finite field, because it was based on polynomial interpolation and extending a polynomial to new points, and that requires a field to be sufficiently large. Okay. Whereas, we are now talking about a method, RAND extract method, where we have only two values in my underlying ring. So, that method of randomness extraction will not work for the Boolean ring setting. So, let us see the randomness extraction method for the Boolean ring setting. So, each party Pi here will pick a random value Qi, which is going to be a bit, because now we are considering the Boolean ring, and it will secret share it among the two parties. So, what we are saying here is that P1 picks the value or the bit Q1, and it secret shares it into two random bits. Secret shares it into 2 bits, that means it picks two random shares Q11, Q12, such that their XOR gives the value Q sub 1, and it acts as the dealer and gives the second share to the second party. And in the same way, the second party picks a random bit Q sub 2, acts as a dealer and secret shares it as per the additive secret sharing. And remember, additive secret sharing here means the addition operation is the XOR operation. Now, what we can say about the two bits Q1 and Q2 which are secret shared by these two parties? One of these two parties is not under the control of the adversary. So, suppose without loss of generality, it is the party P1. That means the bit Q1 which has been secret shared by the party P1 is random from the viewpoint of the party P2, because for Q1 it learns only a share, but what is the other share? She is not aware, and hence it could be any value Q1 which has been XOR shared by the first party. So, now to define the output of this randomness extraction process, we define a linear function. I call that function as G, which takes 2 bits and produces 1 bit as an output, and the output basically is the XOR of the bits shared by the respective parties. So, if Q1 and Q2 are the bits respectively shared by the two parties, then R is defined to be the output, R is defined to be the XOR of those two input bits. And if you see here, this function G is a linear function of the inputs. And now we know that this XOR sharing or additive secret sharing, to be more specific, allows the parties to compute linear functions on the shares of the inputs. So, what are the inputs for the function G here? The inputs are here Q1 and Q2. None of the parties knows the exact means P1 does not know the full value of Q2, P2 does not know the full value of Q1. So, the parties hold only the shares of Q1 and Q2. So, now if I ask the parties to apply the linear function on their shares of Q1 and Q2, they end up obtaining the shares of the output R. That means, if each party just locally performs an XOR of their shares of Q1 and Q2, that will help them to obtain shares of R value, and now I can say that the XOR of R1 and XOR of R2 is nothing but R. That means, I have now generated a value R in a secret shared fashion, and now I can say that this value R is a random value from the viewpoint of this corrupt party P2, okay, or whoever is the corrupt party. This is because there is a well defined bijection between the Qi value among these two Q values shared by the honest party and the output R. What does that mean? Well, since again for simplicity I am taking P1 to be the honest party, this Q1 value is a random value from the viewpoint of the corrupt P2. It could be any bit, it could be 0 with probability half, it could be 1 with probability half. And the way we have defined the output R as a function of Q1 and Q2, for every candidate Q1 which this corrupt P2 thinks in her mind, there is a candidate R. So, if she thinks that okay, Q1 is 0, then that value 0 along with the Q2 shared by P2 defines the R, whereas if she makes the assumption that Q1 is 1, then that 1 value along XORed with Q2 defines the corresponding R. But since Q1 is picked uniformly at random, it could be any Q1 from the viewpoint of P2 which has been now secret shared, and hence it could be any R which is now available among the two parties in a secret shared fashion. So, that is a simple rand extract protocol which works for the Boolean ring case. Now, let us go to stage 2. Okay, that means assuming that the stage 1 has been executed 2L times and we have generated the bits A1 up to AL and B1 up to BL which are random, and now they are available in a XOR shared fashion. Our goal is to now generate the corresponding XOR sharing of the corresponding C values. So, let us do it for just one specific A and B pair. The same method can be executed in parallel L times. So, that means I am assuming that there is a bit A, no one knows the value of A, it is a uniformly random bit and it is XOR shared among the two parties. It has been generated by stage 1. In the same way, there is a uniformly random bit B which has been generated by running the protocol rand extract, and both the parties P1 and P2 have their respective bit shares for the bit B. And now somehow they want to interact and obtain shares, a bit shares C1 and C2, so that it XORs to C, where C is the AND of A and B, and in this process nothing about the exact value of A, exact value of B should be revealed. Okay, that is what we want to ensure. So, if we have this mechanism can be executed L times for all the AB pairs which we have generated in the stage 1, and that will complete the pre-processing phase. So, let us first try to see a very simple idea which many of you might be tempting to propose, but the purpose of this slide is that we want to see that simple ideas do not often work. Okay. So, what is the AND of A and B? So, I am now not writing down the AND operation. A times B in the Boolean ring context, you should imagine it as a ring operation, AND operation. Okay. So, A times B or the AND of A and B is the AND of these two expressions, because A is XOR of A1 and A2, B is XOR of B1 and B2. If I further expand and rearrange terms like this, let me say that the XOR of the first two expressions here, the first two summands, let it be C1, and the XOR of the last two summands, let it be C2. Now, can this first party P1 compute A1 the value C1? Well, it can compute A1 times B1 because it has both A1, it has B1, but it cannot compute A2 times B1 because even though B1 is with the first party, A2 is not available with the first party, A2 is available with the second party, and we cannot afford to ask the second party to give A2 in clear to the first party, because if A2 is given in clear to the first party, then that A2 along with A1 gives the value of A to the party P1, and that breaches the security requirement. We do not want to reveal anything additional about the A and B values here. In the same way, party P2, she has A2 and B2. So, she can compute A2 times B2, fine, but what about A1 times B2? A1 times B2 is like computing a cross term here, where one of the part is with first party, another part is with the second party, and I cannot ask the first party to give A1 in clear to the second party, because that will now reveal the value of A to the second party. So, even though I can identify here a partial C1 and partial C2, which somehow can be computed, will complete the secret sharing of A times P, there is some cross terms which are involved here, namely 2 cross terms. So, you can imagine here that there are 2 cross terms here which are the source of problem, the computation of A1 times B2 and the computation of A2 times B1. How do we compute it? So, imagine we propose the following protocol. So, since there are 2 cross terms here, we run 2 instances of OT. In one instance of OT, P1 becomes the sender and P2 becomes the receiver, and in another OT which can be executed in parallel symmetrically, P2 can serve as the sender and P1 can serve as the receiver. This is just to ensure that the balance of OT executions is maintained properly, because if you see the OT protocol, sender and receiver, they perform asymmetric computations. Sender has a different kind of computations to be performed, receiver has different kind of computations to be performed, right. So, you could have asked P1 to act as a sender in both the instances of OT here, but just to spread the load symmetrically, I am asking P1 to act as a sender in one of the OTs and as a receiver in another OT instance. So, now we have to decide what should be the messages which P1 should feed as sender and P2 should feed as receiver and so on. So, suppose in the first OT we ask P1 to act as a sender and set these as his messages, and we ask party P2, the second party, to set B2 as her choice bit. So, if you now see closely, the correctness property of the OT will ensure that P2 receives this cross term A1 times P2. Okay. And in this process, if this first party, who is the sender party, if he is corrupt, he does not learn anything about B2. Okay. Why? He does not learn anything about B2 because that comes from the receiver's privacy, because B2 is the choice bit of the second party, and if indeed this OT protocol is a secure OT protocol, then if the first party is the corrupt party, it does not learn anything about the choice bit of the receiver, who is the second party, and hence it does not learn anything about B2, fine. And in the second instance of the OT, we can ask the first party to select his choice bit to B1 and let the second party acts as a sender with these inputs M0 and M1. As a result of the correctness of the OT protocol, the first party obtains the cross term A2 times P1, and a potentially corrupt P2 does not learn anything about B1, because B1 is the choice bit of the receiver here, and if indeed the OT protocol has receiver's privacy, then the second party, who is acting as the sender, does not learn anything about the choice bit, which is B1. And now you can see P1 has, the first party has everything. He anyhow has the ability to compute A1 times B1, and he has obtained A2 times B1 as a receiver of the OT. So, he can compute C1, and in the same way the second party, she has the ability to compute A2 times B2 on her own, and as a receiver she has obtained A1 times B2 as the output of the first OT. So, now if she XORs them, she gets C2. So, C1 is now computable by the first party, C2 is computable by the second party, and now you might say that okay, our stage 2 task is done. But now let us try to carefully analyze this protocol. Does the protocol maintain the privacy of the bits of A and B? And the answer is no, because we are revealing AI times Bj in clear to one of the receiving parties or one of the parties who is actually acting as the receiver, and that may end up revealing the entire A or entire B. How so? So, imagine again a corrupt P2. So, if she is acting as a receiver, then she does not learn anything about B1, that is fine, that comes from the security of receiver from the second OT. But as a receiver, she is learning something about A1 here. Why? Because she is learning A1 times B2 in clear, she is learning this full value, and B2 is also known to her. Now, comparing A1 times B2 and B2, she may end up learning A1. How? Say for instance, if B2 is equal to 0, sorry, if B2 is equal to 1 say, and if A1 times B2 turns out to be 0, then she learns that A1 is 0, because if A1 would have been 1 and in anyhow B2 is equal to 1, then she should have got A1 times B2 to be 1, but since she is getting A1 times B2 to be 0 and her own share B2 is 1, she learns that A1 is 0, and if A1 is learnt by the second corrupt party, she is anyhow having the second share of A, and that along with the first share of A helps her to completely find out what is the value of A. Okay. In the same way, if say the sender would have been corrupt, if the first party would have been corrupt, he learns A2 times B1 in this OT instance as a receiver. Now, he learns A2 times B1, he also have B1. Now, depending upon whether B1 is 0 or not, learning A2 times B1 helps him to find out the other share of A, namely A2, and hence the complete A. So, that is why this method of computing the secret sharing of A times B by running the two instances of OT need not maintain the privacy of the bits A and B, okay, because through one of the OTs as a receiving party, a corrupt receiver might learn AI times Bj, and it may end up revealing the entire A or B depending upon what is her share or his or her share of A or B value. So, what we are going to do is we are going to retain this nice idea. The idea was nice that we expanded A times B and identified some mechanism to ensure that the two parties somehow get the cross terms without learning anything about the other party's share of the bits A and B, but we identified a potential flaw here. So, what we are going to do is we are going to slightly change this idea, and the intuition behind changing the idea is that we are now going to change the inputs of the sender's inputs of the OTs. The receiver's inputs for the OTs, namely their choice bits, will remain the same. So, the second party should participate with choice bit being B2, the first party should participate with choice bit being B1 in the other OT instance, because they are not revealed. Okay. If you see the earlier method where we identified the flaw, the choice bits they were hidden because they were coming from receiver's privacy. Now, we are going to change the sender's inputs in these OT instances. So, the first party where he is acting as the sender, he no longer feeds the input 0 and A1 as his two messages, but rather he now feeds the messages M0 and M1, where the message M0 is a random bit R0, and the second message is the masking or the one time pad encryption of his A share with R0 as the pad. And now, based on the correctness property of the OT, it is easy to see that depending upon whether B2 is equal to 0 or 1, the second party or the receiver of this OT will receive this value. And now, you can see that she is learning R0 XORed with A1 times B2. She is no longer learning A1 times B2 in clear as was the case in the earlier approach. In the earlier approach, A1 times B2 was completely learnt as a receiver of the OT receiver, and that led to the problem, because depending upon the value of B 2 she may end up learning about A 1 if A 1 times B 2 is learnt in clear as a receiver output. Okay. But now we are not letting the second party to learn A 1 times B 2, instead we are letting her learn a masking of A 1 times B 2, where the mask is now completely random, because the mask is the other message and she will not learn the other message depending upon her choice bit. So, depending upon her choice bit, if her bit B 2 is 0, she will learn only the mask, that is completely useless, whereas if her bit B 2 is 1, she learns a masking of the cross term, but the mask is not revealed. So, whatever may be the case, she will not learn anything about A 1, A 1 remains as private as possible. Now, let us see the sender's input for the other OT instance. For the other OT instance, we do it symmetrically. The second party P 2, she picks a random mask R 1. The message M naught is her mask R 1 and the message M 1 is a masking of her A share with the pad R 1. And now again, depending upon the choice bit B 1 being 0 or 1, the first party P 1 either receives the mask R 1, which is useless, or a masking of the cross term A 2 times B 1, but with the mask R 1 which is not known to the party P 1. And now I can rearrange the terms in the expansion of A times B into this lengthy expression. If you see this lengthy expression, then finally R naught and R naught cancels out, R 1 and R 1 cancels out, and then everything reduces to only A times P. But if I rearrange the terms like this, then I can identify the shares of the P 1 and P 2, which can be now computed by P 1 and P 2. P 1 can compute this share C 1, because anyhow he has A 1 and B 1. So, he can compute A 1 times B 1. He is acting as the sender. So, he has the mask R naught, and as a receiver he receive a masked version of the cross term A 2 times P 1. So, he has now everything to compute the first share of C, and using similar argument the second party P 2 has everything to compute the other share of C. And now you can see in this process, irrespective of whether P 1 or P 2 is corrupt, nothing additional about the bits A or B is learnt, and that maintains the privacy of your stage 2. So, this is now original GMW method of computing securely the cross terms. Okay. So, remember the problem was securely computing this cross terms A 2 times B 1 and A 1 times B 2. To securely compute the cross terms, we run here 2 instances of OT, which ensures that now the each of these OT instances take care of one of the 2 cross terms. Okay. So, the cross term A 2 times B 1 is now made available in a secret shared fashion, where the share of the party P 1 is R naught and the share for the other party is a masking of this cross term with the mask R naught, whereas the cross term A 1 times B 2 is taken care where the mask is R 1 and available with the second party, and the first party gets a masking of this cross term with the mask R 1. And that is what is the purpose of these 2 instances of OT. Okay. It turns out that we can instead of running these 2 OTs for computing this cross terms in a secure way in a masked fashion, we can run one instance of 1 out of 4 OTs. Okay, because and that will lead to efficiency. So, let us see how we can do stage 2 using 1 out of 4 OTs, and the advantage here will be that only one instance of 1 out of 4 OTs will be executed instead of executing 2 instances of 1 out of 2 OTs. Okay. So, the idea here will be the following: we are given this setup, this is given, A and B are secret shared, and our goal is to compute a secret sharing of the bit C, which is the AND of the bits A and B. So, I can write the second share of C as a function of the AND of A and B and the first share as per this expression, and based on this idea we can let the first party P 1 to pick his share for the C value randomly. Okay. It does not know the AND of A and B, but it can pick his share for the C value, the resultant C value randomly, and now it prepares a table. You can prepare a table indexed by the shares of A and B that are available with the other party. Now, depending upon the shares of A and B which are held by the other party, in his mind the first party can compute the values of C 2. Well, it does not know what exactly is the value of A 2, what exactly is the value of P 2, and hence what exactly is the value of C 2. He is just preparing this table in his mind. He knows that if the other share, if the shares of A and B that are held with the other party are 0, right. Let us see how exactly this table is computed. So, let us see how exactly the first row is computed. If A 2 is 0 and the B 2 is 0, that means the shares of A and B held by the other party are both 0, then basically this means that the value A which is secret shared is same as A 1 and the value B which is secret shared is B 1, namely the shares of A and B held by the first party. Well, first party does not know definitely this is the case or not. Okay, this is a probabilistic event. Now, if the value A which is shared is A 1 and the value B which is shared is B 1, then what can we say about C 2? C 2 will be nothing but the AND of A 1 and B 1 XORed with C 1, and that is what is the value of C 2 kept in the first row here. Similarly, let us see how the fourth row is prepared. Okay. Similarly, you can run the argument to see the second and the third row. If the other shares of A and B are, if the other share of A and B are 1 and 1 respectively, that means A is same as A 1 complement, because 1 XORed with A 1 is nothing but A 1 complement, and in the same way B is same as B 1 complement. And if that is the case, then C 2 is nothing but the AND of A 1 complement XORed with C 1, and that is what is the fourth row. So, once P 1 set his share of C 1 randomly, he can prepare this table, and now he participates as a sender with these 4 inputs. So, these are his 4 messages M 0, M 1, M 2, M 3, and the second party P 2 acts as a receiver for this OT instances for this OT instance. So, she has to provide 2 input bits, because this is an instance of 1 out of 4 OT. So, her selection bits will be A 2 B 2, and depending upon the value of A 2 B 2, the correctness of the 1 out of 4 OT instance will ensure that she gets the corresponding row of this table which sender has prepared. So, if say for instance A 2 B 2 is 0, then this is the value which gets transferred. If A 2 B 2 is 0 1, then this is the value which gets transferred. If A 2 B 2 is 1 0, then this is the value which gets transferred, otherwise this is the value which gets transferred. And now you can see that indeed the XOR of C 1 and C 2 is A times P. Why the security is preserved here? If sender is corrupt, namely P 1 is corrupt, it does not learn anything about A 2 and B 2, because that are the selection bits, because they are the selection bits of your second party or the receiver. So, receiver's privacy ensure nothing about A 2 B 2 is learned. Whereas, if P 2 is corrupt, then as a receiver she only learns the message or only the rows she is interested in. She does not learn anything about the remaining 3 messages, and that ensures that nothing about A and B is revealed in this process. So, you can make the pre-processing phase of GMW protocol stage 2 more efficient using 1 out of 4 OT instances, because now for each multiplication triple 8B to compute the C component, only one instance of 1 out of 4 OT instance need to be executed, instead of executing 2 instances of 1 out of 2 OTs. So, with that I end today's lecture. Thank you.